Yeah, so it seems that you're already here, Daniel?
Yes, I am here.
So yeah, so we are streaming now, so we can start at any moment. Victor. We cannot hear you. I think there's a problem with your microphone.
Uh-huh.
Ah,
Can you hear now?
Yeah, we can hear you now.
Yeah. Is there any echo? No.
No.
Perfect. So thanks everybody for joining to the last keynote, but I mean, not less important of the day. It's a really honor to introduce René Vidal. René, like, I mean, for those who have grown searching like over Google Scholar, the important people in Latin America who do computer vision, René doesn't need an introduction. So René has been working in our field since very long time. He's from Chile, but he did his PhD in Berkeley, if I'm not wrong. He has collected so many awards. His work is really interesting. He works at Johns Hopkins Universities, and recently he holds a position with Amazon as an Amazon scholar. He's an associated chief editor and in chief of PAMI, which is an important journal in the AI community. And his work lies in the intersection of machine learning, but also with biomedical applications, which are of the interest of many of the people in Latin America. So it's really my pleasure, and I really want to say thank you to René, because right now he's on holiday. So thank you for giving us like this hour to share with us your research and your background with us. Thank you.
Thank you very much, Victor. I just wanted to say that I'm really honored that you have invited me to speak. As you well said, I'm originally from Chile, and I think it's really a great idea what you guys are doing, and I'm in full support. So anytime you need anything for the Latin community, I'll be there to help. So thank you again. And if you have any questions, don't hesitate to interrupt me as I move along. So, as Victor said, I am in various places at the moment. And so I chose to speak about two of my different works. Much of this talk will be about the work that I do at Johns Hopkins University, in particular, this topic of semantic information that I've been working for the last 5 years. But I do hope to spend at least the last 10 minutes of my presentation today telling you a little bit of what I'm doing at Amazon, which is, of course, a work that is a little bit more applied. So let me begin with this work. It's really, I think, the work of my student, Aditya, and collaborate also with Benjamin Haefeli. And Don Gieman, I think he's been pushing for a research agenda of this sort for a very long time. So I think he also deserves great credit as one of the brains behind this. So a long time ago, in the 1950s, someone called Claude Shannon invented information theory. And the way by which he did it was by postulating that we could take signals, we could transform them into bits, send them through a channel, and then we could take those bits and reconstruct the original signal. And his idea really were well ahead of his time. They revolutionized communication. Much of the way that most communication devices work today is based on Shannon's principles. But if you think about it, the way in which Shannon envisioned the compression of data, it was independent of the content of the signal. There was no semantics built into it, right? An image will be compressed more or less to the same number of bits, regardless of whether I'm trying to do recognition or object detection. So his work was really independent on the semantic content and independent on the task. And this aspect, which I just mentioned, is not something that people didn't know at the time. In fact, Weaver had already mentioned that much of Shannon's theory was really the technical aspects of communication, but everything about semantics, what is the meaning that the symbols being encoded convey, was not part of the original theory. Some scholars, like Bar Hillel and Carnap, proposed already in the 1950s a way of developing a theory of semantic information that would capture this semantic content. But at the time, much of the work was done based on logic rules, as most of AI at that time. And as opposed to what we would do today, that would be primarily based on signal processing, machine learning, statistics. And much of the state of affairs sort of remained the same up until the 1980s. So why would we care about coming up with a theory of, making all of these semantic? So the reason is that while Shannon theory is perfect for transmitting a signal, for reconstructing it, it's not really perfect for recognition, which is, for example, what we do in computer vision. In particular, think about how would you compress an image when the goal is to do, say, 3D reconstruction versus when the goal is to, say, detect an object. If the goal is 3D reconstruction, then you might care about the viewpoint, but you might not care about, say, lighting conditions. But if the goal is recognition, then you don't care about the viewpoint or lighting. So the idea of compression or the idea of extracting semantic information would care or would change depending on what you want to do with the data. So and these are a few examples that I've already given, right? The same is true for speech. Different people might say the same words in different ways, and the meaning might be the same, but the way in which we say it is different. So any theory of compression that is for the purpose of capturing the semantics has to sort of get rid of these nuisance factors that are not relevant for the task. So this motivates the question of how do we define measures of information or representations of the data that are ideally invariant to these nuisance factors. The second aspect that makes semantic information different from regular information is the fact that there is context. So these two images here have identically the same pieces, but they are arranged in very different ways, and they actually depict two distinct objects. And this is something that Shannon's theory would encode in the same way because it doesn't capture the fact that these are two different objects. So the key question is then, how do we develop measures of information and data representations that capture these rich semantic contextual relationships among scene entities? I won't be spending too much about this because we have not done it fully yet in the multimodal setting, but you could also imagine the question of, well, for a particular task, well, what is more informative? Is it audio? Is it the image? Or is this region of the image? Or is it this word? And so you could also ask the question of different modalities may convey more or less information for a particular task. So any notion of information may also need to reason about which modalities are more important, or how do you capture maybe different scales of one modality, either in
We're having some audio issues, or is it just me?
Yeah,
Yes.
it sounds good.
Yeah, it's okay.
Yeah, I can hear you.
And
That's good.
the semantic content depends on that. So with that introduction, I think I would like to state the goal of our work, which is primarily the idea of developing a information theoretic framework that is able to quantify semantic information in complex data. And as I said, the reason why we want to do this is to assess which features are more informative, which modalities are more informative for a particular task. Another aspect that this could be useful for is it could help us assess the complexity. In various ways, we could think of the notion of entropy as a notion of complexity of the data. And if we had a notion of semantic complexity, it may help us assess which tasks are harder than others, or maybe even have a distance between tasks. So with that in mind, and at a very, very, very high level, the main idea behind what I'm going to be describing is the following. We're going to begin with data on the left, and this could be multimodal data. And we have some task, classification, detection, scene parsing on the right, and that's denoted by Y. And the goal is to build an intermediate representation that is semantic. And if you think about deep networks, of course, they do build intermediate representations, but by and large, they're latent. And if we want to build a representation that is more semantic, we need to constrain that latent representation to capture what is relevant for that task using words or using language that really characterizes the semantic of the task. And so we want that representation to be minimal or as small as possible, but we want it to also be sufficient for making predictions about the task. And that's sort of going to be the high-level philosophy of what we're going to be doing. So the presentation will be divided in 3 parts. The first one, I'll tell you what is a definition of semantic entropy that we have proposed. And this requires you generalizing what do I mean by beats? How do I make beats semantic? Coding, right? An important part of Shannon's theory was that you needed to build a code for every signal. So what is the meaning of semantic coding? And with that, I'll be able to introduce the concept of semantic entropy. Once I've defined it, the key issue is going to be that it's really going to be intractable to compute. And so I'll be presenting first an algorithm that is based on 20 questions that is able to implement the calculation of semantic entropy in a way that is more efficient. And that's still not going to be enough. To be able to do it, we will need generative models, and we're going to be using deep generative models such as VAEs. And so the actual implementation combines VAEs and normalizing flows to be able to do efficient sampling. And I'll conclude, this is something very new, something completely different from what we usually do in computer vision. So because it is computationally very challenging to do, I'll begin with the simplest possible task I can imagine in computer vision, which is just classifying binary images. Yet already you will be able to see that the notion of semantic entropy that I've defined is able to provide a measure of task complexity. I'll be able to show you that classifying MNIST digits, for example, has a complexity that is smaller than classifying, say, the fashion MNIST dataset, sort of suggesting that the fashion MNIST classification task is more complex than that of the MNIST. And why that is possible, it's still speculative, but I hope to convince you based on the results I'll present. All right. So with that in mind, let me get started with the first part, which is the definition of semantic entropy. Before I do that, let me just have one slide about the basics, the simplest concepts behind Shannon entropy in 1950. So usually you begin with some vocabulary or some set of symbols. In this case, the simplest is to assume that they're just discrete. I have n symbols that I care about. And for each such symbol, I have the probability of occurrence. So x is a random variable and pi is the probability for that symbol. So the way Shannon defined information content as measured in bits is simply the log of 1 over the probability. And as you know, the key idea was that rare events are very informative. So if the probability is small, the event is rare and this information content is high. But very common events that have large probability are less informative. And that was the basics. And then the way by which you define entropy is by taking the average or the expectation of the information content. And so that's exactly here, the sum over all of the symbols of their probability times the log of 1 over p. So the expected value of log of 1 over p. All right. So second aspect is not only to define what entropy is. I think we all know this, right? We use entropy all the time in computer vision and in machine learning. At the time, because the goal was to use this as a means of transmitting signals, you also needed to come up with an algorithm that would encode the signal, and that was Huffman coding. And I'm not going to get into the details of how this was done, but the gist of it simply is that naturally, if a symbol is very, very common, you want to put a code that is very short. And if a symbol is rare, then you can afford to have a longer symbol. And the goal was transmission, so you wanted to transmit symbols with the smallest possible code. And so that's the intuition behind the construction of Huffman. And even though it didn't need to be optimal, it really, in a sense, sort of minimizes the entropy almost. And this is exactly the main theorem of source coding that says that the average length of this Huffman code is within 1 bit of the entropy. And so that's sort of connect coding to entropy. And these are the basic results from the 1950s. Has there been anything in between? Of course, there's been tons of generalization and different notions of information, but let me just point out a few recent ones that are actually they served as a lot of inspiration for us. So one was the work of Stefano Soatto, who introduced the question of building representations of data and building them in a way that they're sufficient, by which he meant as informative as the data, invariant, so that they begin to discount these nuisance factors that I mentioned before, and minimal in the sense that are simpler than the data. So there is compression, but they need to be sufficient for the task. And so I think we are going to draw a lot of inspiration from his ideas. Tishby, in 1999, proposed the information bottleneck that actually captures both of these concepts from Stefano's work, at least theoretically, where he says that we would like to learn a representation Z of the data that is sufficient for Y, but that is as compressed as possible or minimal. And this is done by using this information bottleneck objective that has one term that is the entropy and the other term that is the mutual information. And third, and recently, the drawback of Tishby's work is that maybe you can't compute, you can implement this. It's very difficult to do this for images because computing entropies and mutual information is hard. And so Stefano, together with Achille, introduced this notion of information on the weights of a neural network, W, by assuming that these weights are random. And in a very nice fashion, they were able to connect classical Shannon information with Gibson information. Now, that being said, even though we're drawing inspirations from all of these three works, all of them have a latent representation that is latent, okay? So this is sort of not enough for what we wanted to do, which was to make it semantic. So I think the key philosophical difference with the previous work is that we are going to constrain that latent representation so that it depends on some vocabulary that is specified by the user, and therefore the representation is immediately semantic as well as interpretable. All right, so let me begin with what we do. So just to introduce the notation, X is going to be the random variable that represents the data, or maybe features derived from the data. Y is going to be the random variable that represents what I want to predict from the data. Okay, so X could be images and Y could be the class, for example. And T is the task, which we define the task as estimating the conditional distribution of Y given X from samples of X, Y. And so classification would be one example where I want to predict the class given the image, and I do that with a training set that is samples of both images as well as labels. Okay, so this is very classical. This is what we do. So here are a few modifications that are going to be critical to defining semantic information. The first one is that for a semantic task, there will be a large number of variables that define the semantics. So in computer vision, that's fairly clear. So you could have all of the semantics associated with the scene that could include the objects, relationships, lighting, whatnot. And they're defined via some vocabulary that the user specifies what is relevant for that task. Now, the reality, though, is that there's going to be some variables that are going to be relevant for predicting Y, and some are other variables that are not going to be relevant. And the example that I gave earlier about illumination conditions, for example, are nuisance factors for, say, object classification. So just to provide an even more concrete example here, suppose that X was a collection of images of street scenes. And the task, suppose here, that is describe all of the objects and relationships among objects that are present in the scene. And I'm putting here the task and the why and the vocabulary sort of together because they're naturally interrelated. So here is exactly what I mean by a semantic representation. A semantic representation here, denoted by Q, is a set of queries, such as the one that are illustrated here. And so in this example, the queries are binary. Is there a person in the blue region? Is there a unique person in the blue region? Is there a person that is carrying something? And like that, you can generate probably millions of questions about the content of the scene, right? So that is what we mean by a semantic representation. And as I said, nuisance factors here could be the viewpoint or illumination, whatnot. Okay. So I will distinguish then on questions and answers, or queries and answers. So queries is the set of questions that I was just talking about. Is there an object in this region of the image? And Q of X is going to mean the answer to that query. So yes or no. Or if it is object detection, right, the set of queries could be the set of all bounding boxes. And then the answer to the query might be the features extracted from that box, okay? Just to distinguish between what the question is and what the answer to the question is. We are going to connect or sort of embed the sufficiency, right? I was always talking about build a representation that is sufficient for the task. So what do we mean by that concretely? Since the task is to predict y given x, what we would like is that the queries are sufficient. So predicting y given x is going to be the same thing as predicting y given all of the x's that agree on the queries. In other words, imagine the collection of all images whose answers to the questions are identically the same, okay? And therefore, what this sufficiency will do is that the answer to the queries effectively are going to determine y. And so you could actually begin thinking that the queries basically define the task, and they could potentially define multiple tasks, because with the same queries, I could answer, I could solve potentially different tasks, right? And so this already allows me to begin with the first thing that I had promised. What is the notion of a bit? The notion of a bit is exactly these queries. And these queries are by construction semantic. So before, in information theory, bits were either 0 or 1, or in thermodynamics, entropy, right, is whether a particle is present in a cube, yes or no. So now, by analogy, the semantic bits are going to be these semantic queries. And what is the code? Remember the question of Huffman coding, right? In Huffman coding, I wanted to take a signal, say my voice, and translate it into a sequence of zeros and ones. That was going to be the code for that signal that was going to be transmitted. So the code in our case is going to be a collection of queries and answers to those queries. And I might not need millions and millions, right? For a particular image, I might only need a few, and I'll come back to that in a moment. So therefore, just to be clear, because this is very important, a semantic bit is going to be these queries, and the code is going to be a sequence of query and answer pairs for a image X in this particular case. All right. So in summary, what is it that I've been saying? That this is the way in which we're going to build a semantic representation. We're going to take an input image, for example, and we're going to have this encoder that is going to map the input image into a sequence of queries and answers, Q1 through Q5, which is potentially a subset of the millions of possible queries that are available in total. And then the idea is that I'm going to have a decoder that is going to map the answers, questions and answers to those queries in order to predict whatever I wanted to predict. So as you can see immediately, this is sort of generalizing information theory, because in information theory, you would map the input signal to the code via Huffman coding. And then you would have a decoder that would map the Huffman code back to the same X that you started with. And so this was important because you could just transmit the code that was a lot more compressed, and then you could reconstruct based on the code. All right, so this is something that I've already said. Given a query, the encoder maps the input X to the code. And note, I have this weird notation here. The code depends on the queries that the user has given me and depends on my definition of that encoder. I haven't told you yet how am I going to construct that E. I'm just telling you that the encoder just does that mapping. So how does the encoder does the mapping? It's going to do it in a sequential manner. So first, I am going to come up with a first query. And that first query is going to be independent of X. It's going to be a little bit like playing 20 questions, right? You have to guess something. And the first question you ask, you don't know anything yet. So you just come up with a query that depends probably on any context you might have, but it doesn't depend on the specific instance X that I'm talking about. But then the second query, you're going to choose it based on the previous questions and answer pairs. And that's exactly what we typically do in 20 questions. And then I stop. So one of the queries is going to be this QStop. And when do I stop? In principle, I stop in 20 questions when I know the answer to what I was looking for. So I stop when the code is sufficient for predicting Y. Okay. And at this level, there could be many, many encoders that do this. And I'm not telling you which one I'm selecting. I'm just defining sort of what are the properties that this encoder needs to have. But now, finally, I'm ready to define semantic entropy. So what is semantic entropy? I hope it's very clear at this moment what a code is, and that the code is constructed based on this encoder. So this absolute value is not an absolute value. That's the length of the code. So you just compute the length, the number of questions and answers. And you take the expected value of that code length across all examples of your data set. All right. And now we're going to choose an encoder that minimizes that expected code length. Very much like what you would do in classical information, except that the code and the encoder is completely different and is semantic because it's based on these queries. So in other words, what is our definition of semantic entropy? Is the minimum expected number of semantic queries about X. And that's the minimality part that I referred to before. But the answers to those queries need to be sufficient for predicting Y, which was my task. And that's the sufficiency part. And as written here, what this means is that for every pair of data and label, for example, I would like the prediction of Y given the code, which is a small subset of things, to be equal to the prediction of Y if I had the whole X. All right. So, going back to Shannon, this would be my reconstruction of the signal based on Huffman code needs to be the same as the original signal, in a sense, right? This would be sort of the lossless compression type of constraint. All right, so I hope this is clear. I define semantic entropy as the minimum expected number of semantic queries about X whose answers are sufficient to predict Y. So with that definition, the next question is how are we going to compute all of these for a real problem where X is images and Y might be, semantic interpretation, so a very complex thing, or object detection or image classification. So that's the next part of the talk. So in general, everything I've said is intractable to be computed. And we are going to take advantage of the fact that even though the number of possible queries might be huge, think about object detection, right? It's the number of classes times the number of all possible boxes in an image. But in reality, if you give me an image, it's 20 questions, right? There will be very few that might be sufficient to produce an interpretation for that image in particular. So therefore, a more efficient procedure is to compute the semantic entropy in a sequential manner, one question at a time. in a way that I select the questions to gain as much information for predicting Y at every iteration. What do I mean? More specifically, I mean exactly the definition of information pursuit, which is a greedy strategy where the encoder chooses the query sequentially in order of information gain. Specifically, the first query, Q1, is selected as the query that has the maximum mutual information with respect to Y. Okay, that's going to be the first one. And that's what I meant at the very beginning. That's what you choose. Next, the second query is also going to be the query that is most informative for predicting Y, but now is given the queries that I have asked so far. And finally, when do I stop? I stop when the queries so far are sufficiently informative, meaning that the mutual information of any query for Y, given all of the queries that I have so far is 0, meaning that if I add one new query, I don't gain any additional information about Y. Okay. So now this is a greedy procedure. Rather than finding the optimal encoder, I've come up with this particular definition of one encoder. So you might say this could be fairly suboptimal. Does it connect at all to the optimal semantic information that I had defined? So this is hard to prove in general, but we were able to have this first theorem that says that if Y is discrete valued function of X, and the set of queries is the set of all binary queries on X, then the semantic entropy that information pursuit is going to compute, remember, the semantic entropy is just the expected number of queries. So you stop after L queries for every image, and then you compute the average, say, over the training set. So that semantic information computed by information pursuit is within 1 bit of the true semantic information that we defined. Okay, so good. Information pursuit makes our life easier and computationally more tractable, but still not enough. And still not enough because still information pursuit is based on mutual information, and computing mutual information in very high dimensional spaces with images is also generally intractable. And not only we need to compute mutual information between queries and Y, we also need to compute this conditional mutual information given the history so far. And that raises also a bunch of sampling challenges, right? Because if you're doing training, eventually you will need to sample and generate your training example. And so this mutual information would be, give me images that, given the history so far, so given that it already has say a person in this bounding box and it has a car in this other bounding box. So as the history gets longer and longer, finding images that satisfy all of the queries that far becomes, you run out of samples very quickly. So the key question here is, what do we do? What assumptions do we make of the relationship between queries and the output that make these calculations more tractable? And so this is what we do. We exploit what I said earlier, that there are nuisance factors. And so the idea is to postulate the existence of some latent nuisance factors that render the queries conditionally independent. So we're going to assume that queries are conditionally independent given those nuisance factors. This is reasonable, at least unless the queries are causally related, but it's reasonable in the examples that I gave earlier about nuisance factors being the pose or lighting conditions are good examples as to why this might be a reasonable assumption. So with that in mind, our goal is to learn a joint generative model for the queries and the task. And we do that by exploiting what I just said, the existence of a latent variable Z that makes the queries independent. And then what we're going to do is to train a variational autoencoder to learn this joint probability distribution of queries and Y. Shortly, these VAEs have a probabilistic encoder that in this case maps the queries and Y to a latent space that is typically assumed to be Gaussian with some mean and some covariance. And then there is a probabilistic decoder that maps that latent vector and the Y variable back to the set of queries. Okay, and that's exactly what we do to train these models. And once we have them, we can compute mutual information via sampling. So to summarize, I've defined some notion of semantic entropy that generalizes Shannon entropy. The computation is generally intractable. We can make the computation easier by using 20 questions. Few questions will be needed for every instance. But then we need to make a calculation a lot more efficient, and we do that by combining latent variable models, VAEs, and I skip many of the technical details. We really do normalizing flows to improve the sampling, combined with classical MCMC. Okay, let me now move to giving you some examples. So we've implemented this for the simplest possible task, and the task is binary image classification. And we've chosen this task because we do need to build these very complex generative models for images. And in this case, binary images, you can just have a Bernoulli at every pixel, so that makes our life easier. You might think, well, this cannot be the simplest task. Everybody can get 99.99% on the MNIST. But we're going to do it in a very different way. And let me tell you the way we're going to do it. You're not allowed to look at the whole image to do the classification. You can only look at bits and pieces. Let's say 1 pixel at a time. First, the most informative, then the second most informative, and so on and so forth. We're actually going to do it with 3x3 patches. So the question of semantic information is going to be, every query is going to be a 3x3 patch. And you're going to select the first most informative patch, the second most informative patch given the first, and ideally, you would like to classify based on very few patches. All right. And the number of patches in this case is going to be our notion of semantic information, right? The length of the code is going to be the number of patches. So let me tell you how this operates, say in the case of MNIST. So at the very beginning on the left, this is just an image from the MNIST dataset. In the middle, I'm going to be showing which patches have been observed. And remember, it's one at a time. And I haven't observed anything, so it's all gray here. On the right, I'm going to be showing you what is the prediction of the digit for this image. And at the very beginning, I have no clue. So it's 1/10 for each one of the digits. And so that's what the blue really means. And as it gets picked, I should get red for one of the digits ideally. So first query, this is the most informative patch for classifying MNIST digits given this input image. And so this patch gets selected. It's on the 2, so that's why it's drawn as white, okay? And now you can already see that 0 and 2 and potentially 6 and maybe 8 have a higher probability than the other digits. But the system with just one patch is not sure yet. A second patch is observed. This time is in the background. And now the 2 is a lot more picked, but still there is uncertainty. Now a third gets to be chosen in the background, a fourth, a fifth, and so on and so forth. Now the algorithm is, it actually thinks that it's a 0 more than it's a 2, but both 0 and 2. And, if you're only observed the 6 patches that you've seen so far, right, a 0 would be very consistent with those 3 white patches that you've seen. But so would be a 2, right? So that's why there is uncertainty in there. And so now one more is observed, effectively that now is less compatible with a 2. And indeed, once you pass that stage, eventually it really figures out that it is a 2. And now the probability of being a 2 is, say, 0.99, and the algorithm stops. Okay? So you can play that game now and run the algorithm on every image of the MNIST data set. And you can ask how many patches did I need to observe? So in average, it is about 12 patches. All right. So with 12 patches, you can determine the class of the digits with 99% accuracy. But now you can play the same game with other data sets. So the k-MNISTs, and now you need 27 patches in order to get 95% accuracy. With the fashion MNISTs, you need 40 patches. And with the Caltech silhouettes, you need 61. That is what I meant by saying that this makes us hypothesize that the complexity of the task increases from left to right because the number of patches that I need to observe in order to achieve some classification accuracy is more and more. Now, to verify that with something that is more controlled, we decided to just take the MNIST and add noise to it, because the idea was that classifying noisy images should be harder than classifying clean images. And we observed that this is indeed the case. So the x-axis here is our measure of semantic entropy as computed by the information pursuit. The y-axis is the classification accuracy in this case. The blue curve is for the MNIST data set. And as I said, roughly with 10 or 12 questions, you get nearly 100% accuracy. But then the orange is MNIST with noise of 0.05. The green one is with more noise. And the red one is the translated MNIST data set. So as you can see, the main point is that, say if you fix the accuracy, let's say the accuracy was 80%, then classifying noisy MNIST images requires more patches than classifying clean images. And that's why we think that this is correlated to the notion of task complexity. So in summary, the key contribution of this work is that we've defined a new notion of semantic entropy. The key idea is to define it based on a set of queries and answers to those queries. And the key idea is that we are going to be defining semantic entropy as the minimum number of queries that I need to ask in order to predict whatever I wanted to predict. We show that the computation is generally intractable, but it can be made tractable by combining information pursuit with deep generative models. And we showed already that for simple tasks like binary image classification, it actually does conceptually what it was expected to do. Of course, there is a lot more work to be done, extending the framework to more complex tasks. How do we handle RGB data? Building deep generative models for that is a little bit the challenge. Not only that, right? We also need to compute mutual information, and we need enough samples, and the sampling techniques need to be efficient for that. And the extension to multimodal data to have both, say, text and images at the same time. All right, I think let me stop there to see if there are any questions. I don't know if I have time to do the 3 or 4 or 5 minutes about Amazon, but I'll entertain questions while I switch from one talk to the other.
Any question from the audience? Yeah, if not, like Rene, I was wondering, like when you were mentioning like connecting multimodal data, what is it exactly what you have in mind? Like, for example, is it you mentioned text and images. Is it like, for example, to attain, try to bring to the codes some test? Or yes. Is it like...
So I think this can be done, at least conceptually, I think it's easy to do. You can simply define queries that are multimodal. For example, you could say, which one is the first word? The next query could be, is there an object in this region? And therefore, because the method selects the most informative query, it's simultaneously telling you which modality is the most informative, but also at what scale. And it can be alternating between multiple modalities. If you were to choose all of the questions from text first, it will probably tell you that text is the most informative modality, or vice versa. So I think that's the way in which we can extend it to multimodal data. So it's all in the definition of the queries.
Any other question? If not, yeah, maybe we have like, do you think that we can make it, Gilberto, for the quick Amazon.
Yeah.
Please go ahead, Rene.
Give me 1 second.
Sure.
Okay, can you see the presentation in full screen mode?
Not right now.
Okay.
No.
Let's see. All right, so as I said, I'm also working as an Amazon scholar. And in particular, I'm working in the visual search and augmented reality group. And in a nutshell, I'm sure you've bought things with Amazon once in your life. It has to do with every purchase that you do with the phone. That is what my team works on. Just to give you a few examples of the type of products that we're currently working on. One of them is helping customers buy furniture. So the idea here would be that you might go to the phone and be able to potentially get suggestions as to what furniture might go well with your own room. So how do you do that? One aspect, and this is already, you can find it in the Amazon website, is the so-called showroom that was developed by the home innovation team at Amazon, where the idea is to present the customer with a large collection of very nicely decorated images. And you can immediately, if you want to generate a large collection, you can immediately connect that to computer vision, and image synthesis is one of the aspects that's going to be there. But then the idea is to also have automatic detection of what are all of the objects that are present in the scene, so that you can actually show all of the items that are in the catalog, what is their price. And perhaps the customer might think, okay, this is maybe not what I wanted. It might also make suggestions as to what are other objects that might be similar and could be replaced to be put in there. And as you can immediately imagine, generative models, as well as object detection, as well as recommendation systems based on images, are critical to doing this. A second example is now view in your room. And this is also something you can do. You can take your phone and you can select, let's say I want to buy this chair. And now you can click view in your room in the Amazon app, and it will show you in real time the image of that chair, how it's going to look once you buy it at the right scale. And it does so by using 3D information about the scene. And you can immediately imagine there is some structure for motion and 3D vision involved in being able to render these images in real time. And that's something you can do today with the phone. Another product is the so-called Style Snap. The idea here is, can I just take a picture of an object that I want to buy, and then now do search in the catalog so that it suggests to me products that are ideally identically the same product I was looking for, or otherwise some similar product. And because these pictures are typically taken in the wild, you can immediately imagine that you might need to do object detection. You also want to do embeddings, visual embeddings of these detected objects. And then you want to do retrieval and connect that with information that is in the catalog about different groups. So there is a lot of work then integrating visual embeddings and textual embeddings to make this possible. And last but not least, I think the next goal naturally is, can you decorate the room? Can I take a scan of a room in 3D space and be able to populate it with a large number of items that go well together? And as you can imagine, this is again very much related to a number of areas in computer vision. For example, you might want to synthesize images, you might want to generate them in 3D, but also you want to capture, say, contextual relationships. You want to capture what items go well together. You might also want to capture a desired style from the customer. And so I just wanted to say that I'm very excited about working on many of these computer vision projects at Amazon. and they all rely on state-of-the-art technology that is being developed in our community. So with that in mind, I don't want to take more of your time, and thank you. Sorry if I went a little bit over time.
Thank you. Thanks a lot, Rene.
Inspiring work.
So happy to take any additional questions if there are any more.
Yeah.
Right.
Anyone from the Chilean community, Matias? He's like, well, Matias is in Europe, so maybe it's a bit late for him now. So thanks a lot, Rene. Like, I mean, we really appreciate that you took the time. So any suggestion that you have, like, for example, with your experience on how to nurture the community, it would be great to hear. Yeah.
There is a question from Pablo Arbeláez asking.
Oh, yeah, actually, yeah.
Have you considered representations that are optimal for multiple learning tasks simultaneously?
Yes, and I actually removed the slides because I was running out of time, but we have done a little bit of theory of the semantic information for multiple tasks, and we have derived sort of the classical inequalities that you would imagine. What if I take one task versus task one versus task two versus the union of the two, and using that precisely to define those distances between tasks. And I think what was interesting, even though the examples are fairly simple, right? The example of binary image classification. The reason why we took those 4 data sets is because the query set is the same, right? It's just 3x3 patches in that case. And so the same framework, the same implementation is able to do we consider each data set as a different task, by the way, in that case. And therefore, with the same framework, we're able to solve all 4 tasks simultaneously, and more generally, any binary image classification that is of a similar nature. And in fact, I think this notion of semantic information makes sense only in the context of multiple tasks, I think. Thank you, Pablo, for the question.
Thank you. Perfect. Thank you, Rene, for your presentation. It was really nice.
Thank you.
Great. Thank you very much for inviting me. It was a really great pleasure, and best of luck with the rest of the conference.
There is a raised hand. Yeah.
Yes, sorry, I cannot turn on my camera. I wanted to know if have you explored like new designs for articles, for example, chairs or new kind of articles between different groups on a vector space, that maybe you find that 2 groups between them, or a certain population or a certain group of people usually buy 2 different kind of articles. There could be something in between this. You could use a generative model that could produce new designs that could maybe, because by exploring these areas between highly demanded products, maybe between the areas of the encodings for these products, maybe there could be new designs that are appealing to humans. Do you think that's useful?
Yes, thank you very much for your question. So I completely agree. The first goal actually is simply you would like to capture the style of the customer. Certainly, designers use a predefined set of styles, but it could be the case that a customer doesn't quite know what his or her style is. And therefore, I think part of the process and the type of generative models that we're building indeed, they depend upon they're expected to depend upon the style of the customer. For example, myself, I was trying to, let's say, I was trying to decorate my own home in the last few months, and we did have a designer. And then she said, well, tell me what you like. And then, I'm just an engineer. I have no clue what I like. But once I see a picture, it's like, okay, I like that one. And so there has to be, I think, a fair aspect, which is to have an interactive process where the customer discovers what he or she likes. And then conditioned on that, you can do the generation of scenes. So that's one aspect.
Thank you very much.
Christian, go ahead.
Thank you. I would like to take the opportunity to ask something. Well, before you were saying this, I was imagining your system like something like the beginning of dialogue systems, right? In the way that we have a query, and then we start to develop like the retrieval process. I have the feeling that if we go for this, this is more like a general question in the retrieval aspect of dialogues. Like, I have the feeling that when we look at the language modality and the vision modality, the networks tends to overfit to one of the modalities without taking the knowledge from the fusion of these two modalities. Probably because the lack of information in the data set, or because of the model of itself is biased to one of them to answer the question. So have you seen the same, or do you think that is something that we can solve in a way?
So we have not done the multimodal case yet. So everything I'm going to say is speculative based on what I think it's going to be without experiments to back it up yet. But I conjecture that, for example, in the idea of using small patches, or the idea of having very fine-grained queries that only ask for bits and pieces, as opposed to giving the whole information all at once. I think that forces the network to really focus on what small bit is the most relevant and the most informative, the one that is going to help me the most. And so when you think about 20 questions, right, when you ask something, what would be the first thing you would ask? You would never ask, are there 3 people out of which 2 of them are holding hands and the third one is, right? A very sophisticated, right? You would begin with very simple questions that ideally partition the space in 2, right? And those are the ones that are the most informative. So therefore, I conjecture that if we could do everything I've suggested for very rich and complex and multimodal data sets, by designing the queries to be sufficiently fine-grained, we would force the system to really learn what bits and pieces are the most informative. Again, we need to do the work to demonstrate it, but that's my intuition of what's going to happen.
Thank you.
Thank you.
Carlos, you have a question as well?
Yeah, thank you, Professor Rene, for the great talk. I only have one question about your work on Amazon. I was wondering, what do you think are the main challenges when generating this 3D visualization to show, for instance, a chair, how a chair will look on your house? Yes. Because the 3D generation are computational, maybe expensive for a phone. I don't know where you talked on that.
Yes. So there are many challenges. I guess you can immediately imagine, right? If the room was empty and I just had a couple of walls and the floor, then rendering a single object, the main challenges are to make sure that the object is not crossing the wall or crossing the floor, right? So to position it in a way that it respects the geometric constraints. But what makes it more challenging? That in reality, the customer might be showing a number of extra objects that are present, and you need to be able to do the reconstruction of those objects. then you need to make sure that the objects don't occupy the same volume or that you respect the occlusion constraints depending on viewpoint. So all of those are aspects that make it very challenging. Or say, if the customer wanted to say, I want to remove this couch and I want to buy another one, right? How do I render that? If the new couch is a little bit smaller, then there'll be holes in the, and so all of those questions about missing data are other aspects that are also some of the challenges.
Great, thank you very much.
Well, thanks a lot. So I think we can conclude the presentation part of the workshop and proceed with closing remarks. Thank you a lot, Professor Vidal, for your presentation again. And thank you to all the speakers, panelists, and other participants of the workshop.
Thank you. Thank you, all of you.
So I will try to share my screen. Last time at CPR, for some reason it didn't work. Can you see my screen?
Yes, I can see it.
Okay, perfect. So, well, the time has come for the closing remarks. We captured this image in the morning, just to make it different from the opening remarks a little bit. So, as you all know, Latinx and artificial intelligence has been working for some time to be able to develop the careers of newcomers to the artificial intelligence field. And we are trying to nurture the capacities of people in Latin America and Latinx individuals in general. So we have mentoring programs. We are trying to, we have some very interesting projects that we will disclose in the near future to try to help people to solve local problems. But we also have the mentoring programs to enable people to find a way to study abroad or to work for international companies, and also to the mentoring program, or even the tutorial that Matthias gave today is how to publish in international conferences, right? Because a lot of people in Latin America, for different reasons, don't even try sometimes to go to international conference. Only if maybe they did a PhD in the US, or if they did a PhD in Europe and they came back, maybe they have some contacts and they can afford to do that. But there are a lot of people that don't have these opportunities. Okay, so this is something that we are trying to do. And we have been, I think, very successful. For CVPR, we accepted full papers, and we have some of these papers in the proceedings. For ICCB, we tried to do something small, but at the end, I think it was always a lot more, right? I think we did a lot of things, and we probably in terms of participation, it wasn't as big as the workshop we had in CVPR. But anyway, we had 80 general attendees from around the world. According to my statistics, 65 men and 15 women. I think we can still work a little bit more to try to attract more women. In terms of country of origin, we always have a lot of people from Mexico, like 20 from Mexico, but also a lot from Brazil, like 15 in this case. We have people from Peru, Chile, Ecuador, Colombia, Argentina, Panama. This time we have 5 attendees and 5 people from the US. In terms of level of studies, we have approximately 10 bachelor students, 40 people that either have a master's degree or are pursuing a master's degree. And we have 30 participants that identify either as PhD student or hold a PhD degree. This is only the people that was asking for grants, because obviously we also have the panelists and so on. They are not in these numbers, nor the program committee. It's only the attendees. What else? So then in terms of submissions, we have, was a bit tough to get submissions this time because we didn't have proceedings. And also because I guess people is getting a bit tired of virtual events, but still I think was quite successful. We accepted 15 poster submissions, 2 by bachelor students, 5 by master students, 5 by PhD students. In the doctoral consortium, we had 3 participants, 2 from Mexico and 1 from Brazil. So I think we can repeat that this next year. And so from these presentations, from poster presentations, and from the doctoral consortium, we wanted to give some prizes, even if it wasn't that the selection process wasn't as thorough as with other workshops we have organized in the past. So first of all, I want to thank all the oral and poster presenters, and also the reviewers. This time was mostly done by the program committee, by the organization committee. We asked some external people, but it was mostly done by us. What we took into account for the selection was purpose, context, audience, speaking performance, and so on. We have from all submissions from all areas of computer vision, like learning techniques, clinical AI, medical, biological, and cell microscopy, visual language, and other modalities, visual applications, post-estimation and action recognition, and image classification. And so for the award ceremony, first we will recognize as honorable mention best poster. So then I want to say, sometimes in the past we have given GPUs, for example. Sometimes we have given money. This time we decided to give we decided to give a book, a machine learning or deep learning book. We will contact the authors about their preferences. Okay. So for the best poster, I'm glad to announce the best poster goes to Nicolas Gaguillon for his work translating images into graphs, hybrid graph convolutional neural networks for landmark-based anatomical segmentation. Congratulations, Nico. A really good work, a really nice poster. Also well presented, I have to say.
Thank you, Gilberto.
Yeah, it's also nice to actually this time I didn't have time to put all the authors in the slide, but Nikos works with Enzo, who was part of our panelist in a panelist session. So congratulations, Nicolas. Then for best presentation of the doctoral consortium, we have Williams Lima Costa for his work multi-Q adaptive emotion recognition networks. He works at Boxer Labs at the Universidad de Pernambuco in Brazil. I don't know if you're still in the audience, Williams. I cannot see. But well, we will let him know. Then for the best poster presentation, I have to say this one, I just finished the slide like half an hour ago, because we asked the chairs to go and see all the posters. Some posters were really nice, and actually we try to avoid conflict of interest, because actually the winner is part of the organization committee. Congratulations to Carlos Hinojosa, who was helping as part of the program committee for the best oral presentation for learning privacy preserving optics for human pose estimation. He is working in Colombia, but also this was part of an internship he's doing at Stanford with a group of Juan Carlos Niebles. So congratulations, Carlos. A really nice presentation. And,
thank you very much.
Yeah, your poster was crowded all the time, so it was hard to decide. Then I want to thank the organization committee. Seriously, doing virtual stuff, virtual conference like this one is very tough, very time consuming. Especially at the end, right? Towards the end, towards the date of the workshop. It takes obviously every week we have a weekly meeting, and obviously we have to put some part of our time to do this. Javier was working on the social media, so I want to thank Matías Maldenegro from the German Center for Artificial Intelligence. I want to Ulises and Fabian as sponsors. We have great sponsors, and I hope we can get more sponsors in the future. So we really appreciate your effort. Also, Lourdes Martinez and Tania Aguilay as tutorial chairs, helping. I think we have 2 very nice tutorials. Matías' tutorial was very crowded, so I'm really happy for that. Sorry. Then for problem shares, we had Victor Escorcia, who has been really, he has been doing really good work finding for selecting the speakers. What we do is actually, we ask for nominations from around the world, from all the colleagues and the network, the Latinx and AI network, and then we vote. We get some votes, and then obviously Victor, Christian, and Carlos had to contact the speakers, get everything organized, and so on. So it was really nice work. For Christian Rodriguez, it was especially tough because he's in Australia, so sometimes getting in touch with us was tough. Arranging meetings so we could meet all at the same time. For the doctoral consortium, this is, I think, the first time the doctoral consortium is held in a workshop, in Latinx and AI workshop. So I want to thank Fernando Wario, who works in Italy in the Italian Council for Science and Technology, Iran Ponce, who works at Universidad Panamericana here in Mexico, and my friend and colleague Miguel Gonzalez from Tecnológico de Monterrey. They did a really nice work. For the mentoring program, I think this is one of the flagship projects of our workshop, or all workshops, I should say. So I want to thank Paola Cascante and Lourdes Ramirez Serna from Peru, and Paola works at the University of Virginia. Really good work as well. I think that I really enjoyed it. I spent some time during the mentoring hour. It was really very nice, people talking, and a lot of questions was asked and so on. So this time was mostly this dynamic. We didn't have like a 2 or 3 month mentoring program because this workshop was smaller in scale than previous workshop, but still I think that the program was a success. Then for the public relations and website charts, we have my friend Christian Mata from Universidad Politécnica de Catalunya working on the website, Javier Sanchez Galan working a lot on Twitter, doing all that posts that you see every day. Lois Santiago did an amazing job with the flyers and very detailed work. So really enjoy that. Josimar from Brazil was helping us with some outreach. And I also want to thank Rodolfo Valente and Eric Tokuda, that we didn't have volunteers this year, but they did all the work you see in GatherTown was done by Rodolfo and Eric, so it was really nice. We really appreciate that, and very, very short notice because the people from the ICCV organization were taking a lot of time to get their virtual spaces in time, so we decided to go for GatherTown, because normally they're doing that in Italy. So congratulations for your work. Then we want to thank our sponsors. First, Google Research as a platinum sponsor. And as gold, we have Facebook AI, Microsoft, and Amazon Science. Thank you a lot to our sponsors for obviously the financial aid, but also for sending speakers, sending people for the mentoring program, and so on. We're really grateful for that. And as Ron's speakers, we have Apple, Salesforce, and NVIDIA. Thank you a lot to all these companies. I also want to acknowledge the amazing things that our mentors have been doing through the time, and especially for this workshop. We have Jiavian Huang from Facebook Virtual Reality Labs, Cristina Armato from Google, Cristina Vasconcelos from Google Brain, Juan Carlos Nieves from Salesforce and Stanford, Miguel Bautista from Apple, Dennis Villagomez from Amazon, and then Juan Carlos Guevara from IBM Research. Sorry, I forgot the names. Vicente Ordóñez from Rice University, Martin Bray from Google, and so on. Andy Brook, I also think that he attracted a lot of people to the mentoring hours. So we really appreciate your time and all the feedback you gave to our participants. And then an announcement, we are about to submit the application for Latinx in Computer Vision at CVPR. There's a second edition at CVPR and the tier workshop. And so we are repeating as general chairs, Nils Murugarra and me. The thing is that we want to have a tiered junior let's say, general church, so we can keep with the efforts. We don't want to monopolize this organization all the time. So I hope we can see you in person. I hope in New Orleans next year. And if not, we'll do it virtually. But I'm really looking forward to meet you in person, because we have been working for 2 or 3 years already. So it will be great to meet you in person. Okay. Then we're about to start the social hour. We have in this area in the south 3 areas. And you want room 1, let's say, just for hanging out. If you met some people there and you want to discuss something, then you can go to that area. Then we have 2 thematic areas. One in room 2, in which we want to discuss any ideas you have for future iterations of our workshop, any recommendations you have, if you want to join as part of the program committee, you can discuss that. We can discuss that maybe. And also we want to learn more about the computer vision ecosystem in Latam, like the roundtable we did, but more with maybe with the students or young researchers, how we can enable you to do more interesting things, okay? We created some guidelines because ICCB will continue the rest of the week, so we prepare some guidelines about how to network effectively, so you can use that information for that. And I think that's all from me. You can follow us on Twitter, LinkedIn, Facebook, or contact us via email. Thank you a lot for being here. And thank you to all the people that made this possible. Thank you a lot. And I will stop sharing.
Thank you.
So I will see you in a moment. I will grab, even if it's Monday, I will grab a beer and see you in the social hour. Thank you. Congratulations to the winners. We will contact you soon.
Thank you.
Have a nice day, and see you in Gathertown. I think William de Lima was actually still there. You're still there, William. So congrats.
Thanks, everyone. Thanks for the help. Thanks for the help during the registration. I appreciate this. Thank you.
Perfect. Have a nice evening all, and see you in CVPR. Or maybe some other.
See you guys.